Logarithm. I know many of the students are afraid of this chapter logarithm. I'm doing a simple experiment over here to explain you in a better way. Let me try. We generally measure the things with a certain scale which are linears in the nature. That is, we majorly measure with the scale which has more than 1 with the unit distance 2, then 3, then 4, then 5, then 6. The distance between them is a unit distance, right? Now the measure is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have generally seen our scale in our life with these measurements. Now if you have to measure a very big quantity with this scale, it's difficult for me to measure it. Or if I have to compare a very big quantity, say 10 raised to power 5 or 10,000 with the 1, so I require a very big scale to measure it. Suppose if these numbers which are done to the exponents, suppose that there is these numbers, let's say 1, 2, and 2 into 2, 4, 4 2s are 8, 16, 32. If I write this number at the equidistance, then these numbers are in the exponent form, or they are exponentially increasing, right? The exponential factor or the base, which termed here is a base here is 2. So this is a 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. If I scale with this number kind of numbers which are increasing exponentially, here I can measure the big quantities. So 1 indirectly I can say 2 raised to power 0, this is 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, 2 raised to power 4, and 2 raised to power 5, and so on. And suppose if I require a very big scale also, so I just change this base. This is here the base was 2. Let me change the base with the 10. 10 raised to power 0. The next number 10 raised to power 1, 10 raised to power 2, 10 raised to power 3, and so on. That means the base changed from 1, 10, 100, 1000, and 10,000, and so on. So I say at the 4 unit distance, after the 4 unit distance, I get the value 10,000, right? So if I have to measure the quantity, suppose quantity 3433, 3433, therefore this 3433 lies somewhere between here 1000 and 10,000. So this is the way to measure, to mark out the bigger quantity with the smaller quantity onto a same scale. We require this kind of things. So the more the bigger number we require, we increase the base. Here the base was 2, numbers are 1, 2, 4, 8, 16. Here the base is 10, number of 1, 10, 100, 10,000. You can use the base 100. If you use the base 100, then the numbers would be a very big one. So this kind of a things, now these things are increasing the exponential way. These all are the exponential things. And to handle this kind of a things, we require the logarithm, right? Or in other words, let me say the basic definition of logarithm is, we represent logarithm like this: log a n, which is equal to x. This means this is equivalent to a raised to power x equal to n, right? The logarithm of a number n to the base a is the exponent indicating the power to which the base a must be raised to obtain the number n, right? This number is designated as log a n equal to x. Now anything that is power to x, a raised to power x, we are getting n. In the logarithmic way, we write in this way. We are not aware about the power, we write in this way. So if I look again at the scale, this is again written into the logarithm. So I can say 2 raised to power 0 is 1, 2 raised to power 1 is 2, 2 raised to power 2 is 4, 2 raised to power 3 is 8. Now if I say this is logarithm scale, so this 1, 2, 3, 4, 5 is nothing more than that. It's like 2 raised to power 0 is 1. I'd say log 1 to the base 2. 1 base here is 2, 2, 2. 1 to the base 2 is 0, right? Log 2 to the base 2 is 1. Log 2, 4 to the base 2 is 2. 0, 1, 2, 3. Now again if I write this 8 to the base 2, I get 3. 16 to the base 2, I get 4. 32 to the base 2 is I get 5. So in this way this logarithm comes into the picture. More precisely and more effectively, let me explain you again the logarithm here. Here let's say a raised to power x is n, and completing the definition, a should be greater than 0, a should not be equal to 1, and n is greater than. I know this is not easy to digest this kind of a thing. A greater than 0, a not equal to 1, and n is greater than 0. Let me give an example over here. A raised to power x is n. Let me say a be a 2 number, 2, n equal to n. A raised to power x, x is a variable, and here is the n. Say if I say 2 raised to power 0, I'll get the value 1. 2 raised to power 1, I'll get the value 2. 2 raised to power 3, I get the value 8. 2 raised to power 2, I get the value 4. 2 raised to power 3, I get the value 8. Right? Now, the factor we are understanding is I'm increasing the value 0, 1, 2, 3. That is the integer form. I'm getting the value here 1, 2, 4, 8. What about the value here is 1, 2. There might be have 3, 4. There might be have 5, 6. So the value 3 here is 2 raised to power x. This x must be between 1 and 2. Right? This x must be between 1 and 2. 5 and 6 something between 2 and 3. The value of 5 and 6 is between 2 and 3. So the variable part here is x. So I need to equate the x with something. This a raised to power x equal to n is an equation. This is the power x. If I have to rewrite this equation, I have to use the word logarithm. X is equal to log a to the base a and the number is n. This number n. So in this way I can write. Now logarithm of writing this is 2 raised to power 0 is 1. It means log 1 to the base 2 is 0. 2 raised to power 1 is 2. Way of write is this 2 the base is 2 is 1. Right? 2 raised to power 3 is 8. I can say log 8 to the base 2 is 3. Now this is the quantity. This quantity is called the base, right? Logarithm and the scale also. This is the result and this is the variable x 0, 1, 2, 3. Right? This is the way to write logarithm. Now coming to the picture and let's talk more about the base. Let's more talk about the base. We said that a should not be equal to 1 in a is greater. Why we said that? Because when a is greater than 1, that means a raised to power x is 1. A is 1 raised to power x is n. X can be any value. We will not determine the x. X can be any value. We will get the value as 1 itself. So we generally says a should not be equal to 1 because we are not getting any value of the x over here. And similarly, we will not say that the a should be negative. A should be positive and not equal to. In general, whenever we arrive the logarithm, in generally we use the logarithm scale or we use the base in the logarithm as 10. Whenever there is nothing written in the question, we assume the base as 10. This is called the common logarithm. Common logarithm in which generally the base is 10. Suppose if I ask you log 100, obviously here is the base is 10 and 10 raised to power 2 is 100. Log 100. So if I ask you what is value of log 100, nothing is given here. By default the base is 10. Now 10, 100, answer here is something value 10 raised to power x to get the value 100 is what? X is 2. So here the answer is 2. And there is one more base which is called the natural logarithm. Natural logarithm. The base here is called e. The value here of e is irrational value which is between 2 and 3. Approximate value of e is 2.7182, right? And the way we write log any number say 3 to the base e can be written as ln 3. If the word ln is used, it means the base is e here, right? This is the natural logarithm. If we said that log 10 to the base 1 is 0 because 10 raised to power 0 is 1. Log 2 to the base 10. 10 raised to power something which gives value 2. Now this is the very new thing for you. Now, and so on, log 3 to the base 10. Something 10 raised to power x which give you 3 value. And so on. If I say log 10 to the base 10, value here is 1 because 10 raised to power 1 is 10. And so on, log 100 to the base 10 is what? 2 because 10 raised to power 2 is 100. 10 raised to power 2 is 100. Now, important thing learning over here is 1, 2, 3. Now the value here is 2, 3 is value between 0 and 1. That means log 2 and log 3 has certain value which is between 0 and 1. And then from 10 to 100, 10 that means 11, 12, 13, 14 up to 99, the value is between 1 and 2. So this is a very important thing. Value of log 11 to the base 10 or log 15 to the base 10, then 95 to the base 10 is the value between 1 and 2, right? For practicing the things, you must remember the log 2 to the base 10 is Value here is 0.3010, or use the logarithm table. Log 3 to the base 10 is 0.4771. So remember these two quantities, get the other quantity. Now we'll study about the principal properties of logarithm. Principal properties of the logarithm. Let's study about the first property, log a m into n. Log a m into n is equal to log a m plus log a second. Log a m upon n is equal to log a m minus log a n. Now before moving ahead, let me explain you with some certain example here. Log 2 m into n, say 4 into 8, right? This should be equal to log 4 to the base 2 plus log 8 to the base 2. Let's check. This quantity 4 into 8 is 32, right? Now 2 raised to power something which gives you 32 is 5. 2 raised to power something which gives the value 32 is x is 5. Therefore the value here is 5. The value here is 2 raised to power something equal to 4 is 2, and 2 raised to power something equal to 2 raised to power something which is gives the value 8 is what? 2 raised to power x equal to 8. That means x is 2 plus 3. Now obviously 2 plus 3 is equal to 5. Therefore we verified this theorem or this identity as true, and similarly it can be taken for the division also. So whenever you get the two quantities, we can separate them out in form of addition. Now important thing over here is m into n. This is the product and this is the division, and split it out into the addition and subtraction. This is a very important here. It means multiplication and division is split it out into the addition and subtraction, right? Now next is third one, which is we call as base change theorem or base change. Log a to the base m to the base a. Suppose while doing the problem we have arrived that we are not able to solve the problem, we need to change this base, because in addition and subtraction we least saw the last time in the multiplication and division we saw that the base is common here. So in this addition subtraction the base is a here, the base is a here, base is a here, because whenever we deal the problems base should be same. Suppose there is a problem, base of certain logarithm is not equal, what we have to do, we have to change the base into the required base. Now this is the base change here. Now in the base change what we do is log m, here is a, we put the base whichever we need. Suppose we require the base b, we put here this, then again we divide this equation with the number a to the base b. Now this is the value, these two values are equal, here we change the base to the b. In this way we can change, or let me teach you the learning way, how you learn this. What you have to do, m to the base a, you put the line here, put the base b here, and put the base b here. Now this is log b to the base m, log b to the base, right? Third. Now fourth thing is log a m into log m a is 1. Log m to the base a and log a to the base m, if we multiply these two quantities we get the value as 1. Or we can say that log a to the base m is equal to log m to the base a 1 upon. How can you say that? Using this third formula. Imagine how you use this to get this value. Try to change the values from a to m, you'll get this result. The fifth important property here is a raised to power log a to the base n is, if sometimes we get the same thing here, the base is a and the exponent again a is, you get the value n. So this is the required results. And sixth important thing is log m to the power n to the base a is equal to n log m to the base a. That means if you have a quantity that has some power, it comes into the multiplications. And seventh important thing is log a raised to power q and n raised to power p is equal to p by q log n to the base a. This is again very important. So these are the basic fundas of the logarithm. There is one more important which is you require to remember. This is a very good formula over here. p raised to power log a to the cube is equal to p raised to power logarithm to the base a cube is equal to q logarithm to the base a. I'm repeating the 8 point again. P raised to power log a cube is equal to q log a p. It means you have to remember this p and q can be interchanged according to the problem. So these are the very important rules. Let's come to some problems over here. Log a 3 to the base log a to the base 3 is equal to 4. Now the value of a here is a equal to 3 raised to power 4, that is 81, right? Let's do a few more problem here. Find the value of log 9 upon 8 minus log 27 upon 32 plus log 3 upon 4. Now here we use the first and second law of the property. Imagine the first and second law. What was that? Of addition and subtraction. Means I can say the base is not written here. Means by default the base is 10. The important point over here is base is not written. Therefore by default the base is 10. Right? We assume base is 10. Then this are in subtraction and multiplication. Whatever the quantity in subtraction we divided, that is 27 and 32 become 32 by 27, and those on the addition will get multiplied. That is using the log mn features, mn equal to log m plus log n. We have done this. 8 4s are 32, 4 and 4 are cancelled out, 3 9s are 27 and 27 cancelled out. We get the value log 10. Log 1 to the any base, the value here is right. Next one. 2 log 4 x is equal to 1 plus log 4 x minus 1. Find x. Now 2 log 4 x is equal to this 1 plus log 4 x minus 1. Now if I transform this quantity here, 2 log 4 x minus log 4 x minus 1 equal to 1. Now this is has the base 4, this has the base 4. Both have the same base and subtraction. Yes, we can do some applications here. Now this is 2 log. The 2 log x we can say that log x to the base 4. 2 is moved here, that is x square. We know that x is to power n is n log x, right? This was the property again. Now this is the x square minus log 4 x minus 1. Yes, now here is subtraction. Here is subtraction sign, therefore we divide these quantities, that is x square upon x minus 1 equal to 1. Now this is x square upon x minus 1 equal to 1. Now x square upon x minus 1 equal to 4 raised to power 1. That is, now we can solve this. Now this becomes the quadratic equation, right? Now this is x square minus 4x plus 4 equal to 0. That is x minus 2 whole square equal to 0, or x is equal to 2. Now whenever you get the result in solving the equation, you have to verify whether it is satisfying the equation or not, whether the given logarithm is into the negative stage or not, whether the value of base is 1 or not. Now if you put the x2, the base will not change. X2, there is no problem here. X2 means 1, there is again no problem here. Therefore x equals to 2 is the answer for this problem. In logarithm you should remember that you have to check the whatever the answer comes out, you need to check with the original problem. 3 raised to power 2 minus log, let's solve this problem. 3 raised to power 2 minus log 3 upon, I can say 3 raised to power 2 into 3 raised to power minus log. Yes, we can separate it out. Yes, we have separated it out. Now 3 raised to power 2 is 9 into 3 raised to power minus log 3 5. Now this 3 and 3 are the same. Now minus sign. Now if we want to remove the minus sign, I can say this is 5 raised to power minus to the base 3. Now minus sign is reduced. There is nothing here. Now this 3 and 3 are the same. Now we can say 9 into 5 raised to power or 9 upon. Next problem. Log 25 125 minus log 8. Now this 25 125. I can say log 25 raised to power something which is get 125. Now it's difficult to analyze what something 25 raised to power to get the 125. No need to worry. We say this is 5 raised to square, this is 5 cube, right? Minus log 8 is 2 cube and 2 is 2 square. Similarly here, because it's very difficult to analyze what 8 raised to power something to get the 4. Now this is 3. We remembered the formula over here. This is 3. You can take out the 3 here. 2 again, 3 by 2 log 5 to the base 5 minus 2 by 3 log 2 to the base 2. Now 5 to the base 5 is 1, that is 3 by 2 left with. Here we left with 2 by 3 because 2 to the base 2 is 1. 3 by 2 minus 2 by 3 is as simple as that. You get the answer over here. The next thing we'll discuss in the next video about the fundamental logarithm identity and few fundamental logarithm identity and the graph of the logarithm. So how the logarithm vary with the x-axis and y-axis. Thank you for this video. Thank you.